Chapter 13, Conductance and Susceptance. The reciprocal of resistance is conductance, which basically means conductance is equal to 1 over R, and the reciprocal of reactance is susceptance. So B sub C would be 1 over XC, and the susceptance of an inductor is 1 over XL. These quantities are useful in solving parallel AC circuits because they are added as phasors in parallel circuits to form the admittance phasor. Admittance, the 90-degree phase shifts that occur naturally in reactive circuits, dictates how conductance and susceptance phasors are plotted. The basic rules are conductance is plotted along the positive x-axis, capacitance or capacitive susceptance is plotted along the positive j, and inductive susceptance is plotted along the negative j. So here we have capacitive susceptance, inductive, and conductance. Admittance is the phasor sum of the conductance and susceptance phasors. It is also the reciprocal of impedance. So what that means in terms of a formula is impedance is 1 over Y, and Y is equal to the conductance plus J BC minus J BL. So it's opposite that of our impedance for series circuits. Admittance is the phasor sum of the conductance and the susceptance phasors. It's also the reciprocal of impedance, which is what I just drew before. For the basic parallel RC circuit, the development of the admittance triangle is, this is the resistance, capacitive reactance. Here we have a parallel circuit. So the resultant, which again is the hypotenuse of this triangle, is equal to the admittance instead of the impedance. For basic parallel RL, again, here's our parallel circuit. It's just the opposite. You have conductance, susceptance, and again, the resultant is the admittance. So here we have the resistance is 3600, capacitor is 0.01 micro. You still need to find XC here. So all they did here was they said that since XC is 1 over 2 pi FC and BC is 1 over XC, you can therefore say BC is just 2 pi FC. So plugging in the numbers, you get, so here we're going to find the susceptance of the capacitor, and we end up with 94.2 microsiemens, and the admittance is G squared plus BC squared, which is exactly the same formula as our impedance, only you're using the 1 over numbers. And so we get a total of 293 microsiemens. And here is our triangle, 94, etc. And here, if we use an inductor, again we have to find XL. It's 2 pi FL. So BL is going to be 1 over 2 pi FL, and that comes out to 318. Again, same formula. Square them, add them up, and you get the total. In a parallel circuit, you can obtain the current phasors directly by applying Ohm's law or multiplying the admittance phasor by the voltage. For an RC circuit, this second method is, okay, so here you just multiply by the voltage and you'll get the current values directly. In a parallel circuit, you can obtain the current phasors directly by applying Ohm's law or multiplying the admittance phasors by the voltage. So here you have your admittance numbers multiplied by the voltage, gives you your currents. I think that's the same slide. Current phasors. The same relationship between the admittance phasor and the current exists in a parallel RC circuit in this case. So here again, conductance 1 over R, 1 over XL times the voltage will give us our currents. That should be IL. Show the current phasors. Okay, so here what we're doing is we are just, this is a parallel circuit, so they each have 10 volts across them. So take 10 volts divided by The resistance number gives me my current in this branch. 10 volts divided by the X of C. So Ohm's law still relates voltage and ohms. So my ohms is my XC number, and I get 0.94. If I square each current, square root, which is also the hypotenuse of this triangle, I get the total current in the circuit. Or what you could also do is, if you have the admittance values, you can multiply the admittance phasors by the voltage. So here, if you take the admittance multiplied by the 10 volts, okay, so multiplied by the 10 volts, whereas in the other slide we are dividing ohms by resistance, and here it's just the opposite. So the formula to find current will be voltage times the Y numbers. So it will either be BC or it will be G. For a series RLC circuit, combine the susceptance elements first and calculate the total admittance as you did with the simple RC-RL circuits. So then you combine the BC and the BL together to get one number, and you still keep the conductance of the resistor, and Y is calculated from the Pythagorean theorem. So here, now you're ready to find the current phasors as before. It can be done directly by using Ohm's law and the admittance phasors. To find the current phasors from the admittance phasors, multiply each admittance phasor by the voltage. The result is as illustrated. Parallel resonance, like series resonance, is a special case for RLC circuits where XL equals XC, which implies the susceptances are equal. In the parallel case, current in the capacitor and the inductor are equal but of opposite phase. The frequency is given by the same equation as in the other example from the previous chapter. It's 1 divided by 2 pi square root L times C. Ideally, what is the resonant frequency of the parallel circuit? With a 10 nanofarad capacitor and 680 microfarad coil, you just plug the numbers in and you'll get 61 kilohertz. Parallel resonance circuits are characterized by an impedance maximum and a current minimum at the resonant frequency. So this is opposite of what the series RCL circuit was. Like series resonance circuits, parallel resonance circuits also are useful in bandpass and notch filters, as well as other frequency selective circuits. The reciprocal of reactance, it is indicated with the letter B for susceptance. Admittance is the phasor sum of conductance and susceptance. It indicates how readily current can be established. A tank circuit is a parallel resonance circuit.